I certainly want to thank the organizers for inviting me to give a talk in the conference. Dani's papers had a huge impact on my mathematical development, and I also learned a lot about lattices and other basic concepts from talking with him in person at the start of my career and also in later years. In addition, he and his family always treated me very, very nicely whenever I visited Mumbai. So I'm sorry I can't say this in person, but I very much want to wish Dani a happy birthday and thank him for his mentoring and his kindness in all these years. And now I'll try to share my screen, see what happens here. Yep, looks good. Right, so I'm going to be talking about work of Deroin and Hurtado. And if you want the slides, the URL for the slides is at the bottom of this screen, but that's going to disappear after I get to the next slide. So if you want to download it, now's the time. So in order to talk about this work, let's just let G be SL3R. So I think everybody knows that's the 3x3 matrices of determinant 1 with real entries. But if you like, for the experts, you can let G be their work also is true for any semi-simple Lie group as long as it has real rank at least 2. Then we just let gamma be a lattice in G. And it's fine. It's maybe not so great, but it's okay if you're not an expert on this, just to let it be SL3Z or a finite index subgroup. Because what I'm going to talk about in the real case is very interesting, even just for SL3. Well, no, I guess for SL3Z it's known, but so it's not so great, but it gives the idea of what's going on. Anyhow, let's just say, so we've got a lattice. That means it's a discrete subgroup. There's no accumulation points. And the quotient space G mod gamma has finite volume. That's just the definition of a lattice. The Zimmer program, which started 40 years ago and has been continuing up until just recently, is to show that if M is a compact manifold and the dimension of M is small, and there's a specific number for each gamma, for each group, for each lattice gamma, there's a specific number gamma that if a specific number, so that its dimension is smaller than that number, then gamma should not be able to act faithfully on that manifold. And the notation I'll use for that is this funny symbol here. That means that gamma does not act on M. And the Zimmer program is only about smooth actions. Everything has to be by diffeomorphisms. As I said, this started 40 years ago. There are many, many papers on it, but just a few years ago, quite recently, there was a breakthrough. The whole thing was just finished by Brown, Fisher, and Hurtado. Some of the papers have appeared, but there's still one that I think that is still just on the archive. So it's quite recent work, but they completely finished this. It's true. If gamma is a higher rank lattice, it cannot act on a manifold of small dimension, and the dimension is sharp. They know exactly, yeah, it can act on manifolds of a certain dimension and not smaller. But this is about diffeomorphisms. What Deroin and Hurtado did, and what I've been interested in for 30 years, is to talk about actions not by diffeomorphisms, but homeomorphisms. So just continuous actions. And in this situation, we're going to assume the dimension of M is small, but here small is the smallest possible. I'm only going to talk about actions on one-dimensional manifolds. And higher dimensions are certainly interesting, but the trouble is that basically nothing is known. You can get some results if you assume that gamma has some finite subgroups, just because those finite subgroups can't act, basically. But other than that, I don't think anybody's been able to do anything really big on it. So the situation that I want to talk about is we've got a lattice in SL3R, got a one-dimensional manifold. So I think everybody knows that a one-dimensional manifold is either going to be the circle or the line. If it's compact, it's got to be the circle. And the question is whether that lattice can act on the line or the circle on that one-dimensional manifold. I answered this question 30 years ago for the special case where gamma is SL3Z, or actually I put a dot up there because it also works for finite index subgroups in SL3Z. It doesn't have to be exactly SL3Z. And the theorem that I proved, which is quite easy actually, is just that SL3Z cannot act on the circle and it also can't act on the non-compact one on the real line either. There's no faithful action of SL3Z on the circle or the line. But I just did one example. SL3Z was the only lattice in SL3R that I could do. There's lots of other lattices, and it's interesting to ask whether they can act. So looking at lattices other than SL3Z, and if you want, you can look at other semi-simple Lie group lattices and other semi-simple Lie groups. Deroin and Hurtado did. And other people looked at this. So a major theorem for general lattices, not just SL3Z, was proved by Ghys and Berger-Monod independently. They proved that if gamma does not act on the line, then it also does not act on the circle. So what that means is, there's two one-dimensional manifolds, but we only have to look at one of them. We just have to prove that gamma doesn't act on the line, and then the circle comes for free. And the same is true if you're interested in semi-simple groups, unless SL2R is a factor of the group. Well, 30 years later now, suddenly, sorry, no, this is only 20 years later, my bad. 20 years later, we have another breakthrough. This is by Deroin and Hurtado. They proved gamma does not act on the line. No assumptions. Gamma's a lattice. Well, gamma's any lattice in SL3R cannot act on the line. So they took the Zimmer program, at least in one dimension, and solved it. And for other semi-simple groups, there's a condition you have, but no lattice in SL3R can act on the line. That's what I want to talk about today. I'm going to talk about their theorem in this special case, just to avoid some complications. But actually, I'm going to do something else. For the Deroin-Hurtado paper, gamma is always a lattice in SL3R, or they could take some other semi-simple Lie group. But what I'm actually going to explain today is that the same proof works in another setting, and in fact, it's much easier. I'm going to talk about an easier version of their theorem, where a lot of the complications don't arise. So I'm going to present some of the main ideas in the case where I'm going to show that gamma does not act on the circle. Sorry, does not act on the line. That's what we'll prove. We'll prove that gamma does not act on the line. And then by the Ghys and Berger-Monod theorem, it also will not act on the circle, but I'm not going to talk about that. But I'm going to take gamma to be a lattice not in SL3R, but in SL3 of a p-adic field. And maybe I should say this is work in progress. I haven't written anything down, so it's possible that I've made a mistake somewhere. But all I had to do is just read the Deroin-Hurtado paper. Most of the arguments work as written, word for word. In fact, they'd work for any locally compact group that had the right, a lattice in a locally compact group that had the right subgroups, Borel subgroups and things like that. There's a few cases where I had to change some words. And then actually, also, some parts of the paper just you can skip. I'll explain that today, that the proof is definitely easier. There's things you don't need to even worry about when you're doing this case. So I think I have it right, but I'm a little bit worried that since I haven't written down, I've done something stupid. And I think, now this I haven't checked as carefully, although actually, no, but the first thing is, the proof will also work not just for SL3QP, but for semi-simple groups, as long as all of the factors have rank at least 2. And in fact, it should also work. Deroin and Hurtado originally did SL3R, and as I'm saying that it's easy to do SL3QP, well, you can put the two together. There's this I'm not so sure of because there are some details, because the reals are involved. There are some complications that don't show up in the p-adic case, so I haven't checked this carefully. I'm sorry, but I think that should be right. So the idea is that gamma should be the proof probably works. I think it seems to work for any S arithmetic group, as long as there's no p-adic factors that are of rank 1. I don't know what to do if you have a p-adic group of rank 1, but if you have just take a bunch of simple Lie groups and a bunch of p-adic groups, as long as none of the p-adic simple groups have rank 1, it seems that the proof would work, but this I really haven't checked, so I'm not so sure about that. I'm going to focus on SL3QP. And the idea is that this is going to give the ideas of the Deroin-Hurtado proof, but in a simpler situation. So I'm just trying to explain some of the main ideas of their proof. And so, yeah, I'm doing that unless there's objections or questions. So I'm going to talk about some of the main ingredients of the proof. And the first thing is there's something that they call the almost periodic space. So let me explain what that is. It's a theorem originally proved by Deroin, but then he and his collaborators improved it. that if you've got a finitely generated group that acts in a line, and so the way the proof that I'm going to talk about today works, let's assume that our lattice acts on the line and we'll get a contradiction. So we do have an action on the line. Then they were able to compactify that action. The line is not compact. They were able to compactify it in a very nice way. They found a compact metrizable space, a very nice space, which they call Z, such that, first of all, it has an R action. The real line is acting freely. No element of R has a fixed point on Z. And also, just completely separately, there's an action of gamma on Z, which has no global fixed point. It won't be acting freely. We'll see that, well, yeah. Now, this isn't saying anything, but the point is that they were able to connect these two actions. Each R orbit is invariant under gamma. What that means is that gamma is acting on each R orbit separately. And because the R action is free, each orbit is a copy of R. So what's going on here is we've taken a whole bunch of actions of gamma on the real line and stitched them together. Now, what Deroin and his collaborators did was stitch those together into a compact space. So all throughout this space is actions of gamma on R. And then besides this, they were also able to, you're also able to get some additional technical conditions to be true about this space. The main thing is that the R orbits are gamma invariant, so gamma is acting on all these copies of R. But as I go through the proof, we'll need some additional conditions. In fact, a couple of them will come up just in the construction. But I'm not going to talk about all the things you can make true, but we'll see some of these. I'm not going to get technical about it. So let me just give the idea of why this is true. And, well, we know there's an action on R, but the key thing is that they were able to regularize this. This is an action by homeomorphisms, and it's well known that there are examples of actions by finitely generated groups on the real line that can't be made smooth. You can't make them differentiable, but Deroin was able to get it to the next best thing. He was able to make every one of those element of gamma act by a Lipschitz homeomorphism, or even by a bi-Lipschitz homeomorphism. And then also, each element of gamma has bounded displacement. That means if you have a particular element of gamma, there's a number C, so that no element of the real line moves a distance more than C. Neither of these is obvious, but both are true. And then you can get other additional conditions, other nice things if you want them as well. And we'll see a couple of those. But the point is, in order to construct Z, all we need is these two conditions. The point here is that there's some constant, I called it C, so that every element has bounded displacement, has displacement bounded by C, and not every element, sorry. There's only finite many generators, so let's pick a constant so that every generator has displacement. Every one of those finite many generators has displacement less than C, and also the Lipschitz constant of every one of those generators is less than C. Then we just define our space to be the set of all actions on the real line, such that each generator has a displacement less than C. If you look at how far gamma moves any element X, for all gamma, I should have said for all generators and for all X, the distance that gamma moves X is less than C. And then also, I didn't write this down, but then the Lipschitz constant of every generator is less than C, and you can build in some other conditions if you want them. And the thing to think about is, this does part of what we want. This is a compact metrizable space. The point is that if you have a sequence of such homeomorphisms, a sequence of such actions, where each gamma has bounded displacement and bounded Lipschitz constant, well, since there's bounded displacement, if you look at an element where an element of X goes by some sequence of elements of gamma, those will converge. Sorry, no, I shouldn't say sequence of a gamma. You fix a gamma, look at a sequence of actions. All the X is only moving a bounded distance, so it's staying in a compact set. Some sequence will converge, a subsequence will converge. That means that these homeomorphisms, these actions do have a limit. And then the bi-Lipschitz means that the limiting homeomorphism will be bi-Lipschitz with that same constant. And so in particular, the inverse will exist. So these are homeomorphisms with Lipschitz. Yeah, anyhow, maybe I've said more than I need to. This is a compact space. And now, in order to finish the proof, I just want to make an action of R and an action of gamma so that each R orbit is invariant. And the R action is quite simple. The R action is just conjugate. If you have an element of R, it translates the real line by that distance, conjugate by that translation. So let me write that down here. If you have a homeomorphism, so phi is telling us what gamma does. So we've got some homeomorphism phi depending on gamma. To act on that homeomorphism by a real number, apply phi not to x, but a translated version of x. And then after you've applied the homeomorphism, translate back. It should be completely clear that this homeomorphism here has the same Lipschitz constant as phi. And also, if you think about it, it has exactly the same displacement. If you move x to the left by some distance, if you move x left by t, and then move it some distance, if you translate forward by t again, you've moved exactly the same distance as x moved. So this is giving an act. Gamma is invariant under R. So it's, yeah, so we have an action of R. And then we just use that to give the action of gamma. In order to have gamma act, we've got some action defined by a homomorphism from phi to the homeomorphism group of R. I want to tell you what lambda is going to do. It comes from the real action. Simply see where 0 goes under the homeomorphism corresponding to lambda, translate phi by that amount. Translate the action or conjugate the action by that amount, I should say, not translate, but conjugate the action by that amount. It's not so obvious that this is an action, but it's a straightforward calculation. This is an action. So we've got an action of R, we've got an action of gamma, and from the definition, it's clear that each R orbit is gamma invariant, because what an element of gamma does is just translate by just have an element of R act on it. So that's the definition of the space. We don't need the definition for the proof. We just need to know that it exists. So let me see how to do that. How to do this. So the point, all I've said so far is that we have this space called Z. It's the almost periodic space. We have an action of R and an action of gamma, and each R orbit is gamma invariant. Now, standard thing, just induce this up to a G action. Remember, gamma is a subgroup of SL3R, which I'm calling G. Induce to get a G action. So what that means is we're going to let X, I'll call the G space X. X is G cross Z, and then you mod out by an action of gamma. So I'm not saying anything new. I want to emphasize this is not something new. This is just a standard, but it's for people who haven't seen this. So there's an action of gamma on this Cartesian product where it acts on G just by multiplication on the right, and then it acts the usual way. However, we've got an action on the space Z. You just act that way, except put in an inverse to get an action instead of an anti-action. The quotient space is called the induced, it's the induced space, and there's an obvious action of G on that. Just G acts on an equivalence class of an ordered pair by just multiplying on the left. Gamma multiplies on the right, G acts on the left, so it commutes with the gamma actions, so it respects the quotient space, it acts the quotient space. And then if you look at this, it's a basic fact. If you just collapse Z, if you forget about Z here, you'll just get G mod gamma. If you mod out Z, you'll get G mod gamma. So it turns out that this space is a bundle over G mod gamma. And in fact, you can identify it then with G mod gamma cross Z. But the action is twisted. It's not just an obvious action, because there is no action of G on Z. Right, that's classical. Now let's take the next step, though. This is the next thing that Duane and Hurtado do. Standard thing, let's let K be, well, G is SL3 of QP. Let's let G be SL3 of the p-adic integers instead of the field. So this is clearly a subgroup of G. And in fact, since the integers are compact, this will be a compact subgroup of G. In the real case, you just let K be a maximal compact subgroup. Well, that's what this is. This is a maximal compact subgroup. But here, of course, this compact subgroup is open, which makes things much easier here. Since K is open, if you look at G mod K, it's going to be, every point in there is open. So this is a discrete space. And also, gamma is a lattice, so G mod gamma has finite volume, but it's, yeah, okay, let me say, yeah, it's finite volume. It's well known that lattices in p-adic groups are actually co-compact, so G mod gamma is actually compact. Well, if we mod out both, if we mod out by K, it's discrete. You mod out by gamma, it's compact. So it's compact and it's discrete, it's finite. Well, for today, let me just make things a little bit simpler. I've got a finite set. Let me just assume that that set is a single point. So I'm avoiding a little bit of technicalities here, but there's nothing difficult that I'm skipping. But let's just assume that that finite set is actually a single point, and which means that G is just K times gamma. And in that case, if you mod out gamma, on the left, you get G mod gamma, but on the right, you just get K. G mod K can be identified with this maximal compact subgroup. And so that also tells us that the induced space, the G space X, is just K cross Z. And I should say here, maybe I should have mentioned it earlier, this, what I've done in just a few sentences here, is much easier than in the real case. In the real case, you can't just identify G mod gamma with a compact subgroup. In fact, yes, G mod K is not going to be finite. In fact, in the case where G is SL3R, this is a 5-dimensional manifold, and you have to deal with it. You have to, I mean, yeah, that's just something that Deroin and Hurtado had to do. You look at geodesics, look at geometry, work with this space, but none of that is necessary in the p-adic case. In the p-adic case, this is a single point for today, but actually in the general case, I have to work with a finite set. But dealing with a finite set is nothing compared to having to deal with some multidimensional manifold. So this is one place, one of the main places where the proof becomes much easier. And I should say, this is kind of the standard thing in p-adics. Often p-adics proofs are easier than real proofs. And we'll see that here. Okay, so we have the almost periodic space. That's a key thing. We've got this space. The reals are acting on it. It's got an action of the reals. It's got an action of gamma. And then we induce to get an action of G. And the induced space, normally it's G mod gamma cross Z. That's what you see in all the papers. But for us, it's actually just a compact group cross Z. And now let's take a nice probability measure on G. So by nice, I mean compactly supported, absolutely continuous with respect to Haar measure, symmetric. I mean, just, yeah, a nice measure, nice probability measure. And also another nice thing is I want it to be invariant by K on both sides. It's invariant under left translation and right translations. Now, I said on the last page that G is just K times gamma. So essentially, it's just Fubini's theorem. G is a product, K times gamma, so we can fiber it. This measure is going to be, the measure on G is a measure on K times a measure on gamma. And the bi-invariance, or just invariance, tells us that the measure on K is just Haar measure. And then I don't know anything really about the measure on gamma, except there's definitely going to be something nice. It's got finite support. I don't know what else you can say about a measure on a discrete set, but yeah, it's yeah, that's the situation we have here. The measure we took on K is actually breaks up into a measure on K and a measure on gamma. And now let's introduce one more measure. Let's get a measure on Z. It's a probability measure on the almost periodic space. And let's use the structure. We've got an R action. So R is acting on a compact space. There's going to be an invariant measure. So let's take a measure that's invariant under R. And the key thing is what that means is that on each orbit, this measure looks like Lebesgue measure. On each R orbit, we have Lebesgue measure, and those are all put together into some probability measure. Now, this is where I need another nice property. I said that Z was constructed with a few properties, and you can get other things to be true. And here's I need one more. One of the things that Deroin and his corroborators did was to construct Z in such a way that each element of, let me see now, I didn't say that right, yeah. So for each point gets moved by elements of gamma, and the distance it's moved is the displacement. What they proved is you can arrange this action so for every point on the line, and what it says, every point in every R orbit, when you look at what gamma does to it, the mean displacement is 0 if you measure it by the distance. There's an R, each orbit is identified with R in a natural way. If you use that as your identification, the mean displacement is 0. What I mean by that is if you take any point and take the average over all elements of gamma, well, actually, remember, this measure has finite supports. This is actually a finite sum because I'm going to wait later. But if you look at where gamma moves the point, so I got a point, I move it by gamma, look at the distance that it moved, the signed distance, weight that by the measure that we have, that weighted average will be 0 for every point. The mean displacement is 0. From that, it's not difficult to prove that, in fact, this measure Z, this measure on Z, is stationary for mu gamma. What I mean by that is just that if you convolve gamma with mu, not saying the right thing. If you take an element of gamma and apply it to the measure is not invariance. This is probably not mu Z. It's probably some other measure. But if we weight that measure, and so if we take a weighted average of these translates of the measure, that is just the convolution of mu gamma with mu Z. So we take a weighted average of the translates, that will be back to the original measure. Stationary measures are not invariant, but they're invariant on average with respect to this measure. And the reason for that, this is not difficult to see. The idea is just that if you take some interval in the line, when you apply gamma, it's going to move. You apply elements of gamma, it'll move. But this, if you look at the mean, the average place, on average, this point doesn't move. That's this mean displacement 0. And on average, the right endpoint also doesn't move. That means when you average up the lengths of all these intervals you get by applying elements of gamma, the average will be just the same as the original length. So it's an elementary argument to show that any R invariant measure on Z will actually be stationary for the gamma action. And then once we've got a stationary action for gamma, I mean, we've got this nice measure for this, we've got this nice measure on Z. Let's turn it into a measure on X. And it's very, very easy here because X, did I write it? Yeah, X is just K cross Z. There's an obvious measure on K. And now we have a measure on Z. Put those together. Take the Haar measure across this mu Z. That's going to be a measure on X, a probability measure on X. And it's a calculation. It's probably not obvious, maybe, but this measure, because the measure on Z is stationary and the measure on K is invariant, and all of G is just K and gamma put together, it will be a stationary measure. And this, again, is a place where the proof is much easier for the p-adics. In the real case, it's not at all obvious how to get a G stationary measure or a stationary measure on X from a stationary measure on gamma. And so Deroin and Hurtado had to go through some work to do that. But for us, the construction is very easy. In the p-adic case, we cut out all that proof and just write down what the measure is. Right. So we already had this action. We had 2 actions on Z. We had this induced space. And the new thing is that now we have this stationary measure on X. And let me introduce a little bit more notation. I'm still just talking about stationary measures, but a little bit more notation here. This is standard. Let P be a minimal parabolic subgroup, or you can call it a Borel subgroup if you want. It's just the upper triangular matrices. And then we'll let A be what it always is. It's the maximal split torus, so it's the diagonal matrices. And now, that's certainly contained in the, this A is contained in P, clearly. Now, for each element of A, so for each diagonal matrix, I just introduce some notation. This, I think, for a dynamics audience, this is well known. This is my notation for the expanding horospherical subgroup, or for the unstable, the strongly unstable subgroup. It's all the elements of G that when you go backwards in time, if you go backwards in time, the element gets shrunk. What that means is when you go forwards in time, of course, it expands. So this is the expanding subgroup. And it's a crucial theorem, very old, almost as old as I am, that if you have a stationary measure on, if you have a measure that's stationary for G, it comes from an invariant measure for P. For every stationary measure on G, and every G stationary measure, so we've got a measure on X that's stationary for G, there will be a P invariant measure on the same space on X, so that the measure, the G invariant measure, is just obtained by averaging the P invariant measure over K. So we just average over K all of the translates, the K translates of the P invariant measure. That will give you the G stationary measure. And this is one thing where I might have made a mistake here. I hope not. It sure looks right. Furstenburg only looked at the real case. I didn't check super carefully, but it certainly looks to me like the same argument, just exactly the same, works for p-adic. So I don't think there's a problem here, but the truth is, yeah, I'm sorry, this is work in progress. I did not check these things as carefully as I should have before giving this talk, but I believe that's right. Certainly is for the real situation. Stationary measures for G come from invariant measures for P, and essentially this is like the standard thing to say is that this is like the, oh shoot, what do you call it? The Poisson integral representation of a harmonic function. Stationary measures are much like harmonic functions. There's a classical theory of Furstenburg about Poisson, measures of the Poisson boundary, understanding what it is. Same thing works for a measure. Now, here's the key thing. Deroin and Hurtado call this the key proposition, and it is the crux of the argument. This is what makes everything work. The theorem or proposition is that if the expanding subgroup, if you've got some element of A whose expanding subgroup is contained in P, and there's an additional technical condition, you have to assume that A is what I'll call leafwise contracting. I'll explain what that means later, but it contracts on the leaves. Then, in fact, the P invariant measure is invariant not just under P, but also under the entire centralizer of A. That's the key to the whole proof, is proving this fact. That if a measure has two simple properties, it's invariant under something that you didn't know. I will prove this, or at least give the idea of the proof, but before I do that, let me explain why it's so important. We're assuming that gamma acts on R. We've constructed a bunch of things. From this proposition, we can now get a contradiction to show that that action did not exist. Our assumption was wrong. So that's what I want to explain. So I will come back and prove this, but to prove it, I'll have to talk about what contracting is so that you understand the statement. Before I even without even worrying about what contracting is, let me just use this key proposition to obtain a contradiction. The first thing we need to do is just use this. What this really, the contradiction comes from the fact that from the corollary, we see that this measure measure mu p, by definition, mu is P invariant, but this proposition tells us, in fact, that it's G invariant. And Deroin and Hurtado call this their argument for this propagating invariance. That's the idea. We know that P is invariant. We know the measure is invariant under P. We make it invariant something bigger, invariant something bigger, 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 until you finally get it invariant under all of G. That's what we're going to do here. And so let me give the proof, except I haven't even told you what leafwise contracting means. So let me ignore anything about leafwise contracting. Let me just pretend that whenever the expanding subgroup is in P, then the measure is invariant under the centralizer. And the way to do that is just, we have to pick an element A. So let's pick A to have two, it's a diagonal matrix. It's got two very big entries that are equal to each other, and then a small entry, 1 over the product of those at the bottom there. Well, if that is our A, and then A to the n will be even bigger up there and smaller down there, well, it's the expanding subgroup will just be in the right column there. It will be in the last column. It's certainly upper triangular, so it's contained in P. Our assumption is satisfied, so the conclusion is true. Mu P is invariant on the centralizer, and a centralizer, a matrix that has two equal entries on the diagonal, is going to be this upper corner there. And then similarly, we can apply the key proposition with A being something with just one big entry and then two small equal values. In this case, the expanding subgroup will be in the first row, upper triangular again. So the proposition applies. It's invariant under the centralizer, which is the bottom right corner. Now we're done. We've proved that it's invariant under the top left corner and under the matrix in the bottom left corner, bottom right corner. Well, G is generated by these two subgroups. So the measure is invariant under G, all of G, the subgroup generated. So just a couple of comments. First is that this is the only place where we use the fact, I mean, if you talk about semi-simple groups, this is the only place where we use the fact that the groups have to be higher rank. If the group was rank 1, in a group of rank 1, the centralizer of any element of A is basically just going to be A. There might be some, it's contained in P. But we already assumed the measure is P invariant. So proving that an A is contained in P, this is not anything new. Proving that the measure is invariant under A is a fact we already knew. So the proposition is completely useless in dimension 1, in rank 1. But in higher rank, this is a standard superidity kind of argument. You work your way up to get to the whole group. And so there's a problem here. So Deroin and Hurtado, well, actually, yeah. So the problem is that means that since rank 1's a problem, in fact, this argument will not work whenever there is even a single factor of G that has rank 1. So you have to do something really absolutely completely different. It's much more complicated. And I'm not so sure that that argument does work in the p-adic case. In fact, I think it will need, well, I don't know, maybe, I don't know the literature well enough about p-adic groups to know if the facts that they use for real groups are true for p-adic groups. So that's something that I'll have to look at. But definitely this argument is not right, but in a group like SL3QP, it's clear that these centralizers generate. So we get invariance under the whole group. All right, so what am I doing here? Oh yeah, I'm supposed to be showing that I'm explaining why this key proposition gives us a contradiction. And the first step was just to show that it proves that mu, this measure mu is G invariant. And so let me get a contradiction from that. Mu P can't be G invariant. Here's why. Remember the definition of mu P. So mu P came from Furstenburg. Furstenburg tells us that any G invariant measure is an average, every G stationary measure is an average of P invariant measures. P is this, and mu P is this P invariant measure that we average to get this G stationary measure. But the corollary tells us, it's right there, the corollary tells us that mu P is G invariant. That means if you translate mu P by an element of K, nothing happens. This is just mu P. So we're just integrating mu P, not translates of mu P are the same as mu P. But if you integrate a constant, you just get that constant back. So mu X is just mu P. There's no averaging going on if the measure is already invariant, G invariant. But we proved that mu P is G invariant, so mu P is G invariant. So mu X is G invariant. That's what follows from this. That's the point of this corollary. It's not just that the P measure is invariant, but the G measure is invariant. And remember, mu X, we defined it to be just this product. It's har across a measure on Z. And then it's not hard to see from this that if you take the product to get an invariant measure for G, then in fact, the gamma measure, the measure on Z has to be gamma invariant. Gamma is acting on Z, and we're getting a G invariant measure. That had to be invariant measure. And remember, the action of gamma preserves all the R orbits. Gamma is acting on each R orbit. Each R orbit looks like a copy of R. And since our measure, mu Z, is R invariant, as I said before, the measure on each orbit is just Lebesgue measure. So the action of gamma on each R orbit is preserving Lebesgue measure. That means it's just a translation. So you've got this action, just pick any orbit, in fact, pick any orbit. We've got an action of gamma on a copy of R that's acting by translations, but the group of translations is isomorphic to R. So we have a homomorphism from gamma to the group of translations. That means we've got a homomorphism from gamma to just R to an abelian group, but that's nonsense. The abelianization of gamma is finite. There is no such homomorphism. So that's where the contradiction comes from. The contradiction comes from the fact, if you get a G invariant measure, if you prove that the measure on X is G invariant, that's a contradiction. Okay, so the last thing I want to do, I've talked about the almost periodic space. I've talked now about stationary measures. The last thing I want to talk about is the third key ingredient. And actually the paper has maybe another ingredient or two, but these are three of the major points here. The last one I want to talk about is this contracting business, what it means to be leafwise contracting, and then also explain then why this key proposition is true. Okay, okay. So, and maybe I should say leafwise contracting is a name I made up. In the paper, it's called globally contracting because there's a technical issue that actually some elements are only locally contracting, not globally contracting, but I don't need to make that distinction for a talk like this. I'll just call it leafwise contracting. It means contracting on leaves. And the key fact that we'll need, I'll explain what this means, but the key fact is that, well, A is the diagonal matrices in SL3. That looks kind of like the plane. It's two-dimensional. You can think of it as being a plane. Inside that plane, there's a half space where everybody is contracting on the leaves. That's the key fact that gives the proposition, leaves the contradiction, everything. This is what we need to talk about. Let me explain what this means, this leafwise contracting business. The point is that the action gamma X within the leaves, G will not preserve the leaves, but it respects the leaves. If you induce an action that preserves the leaves, every element of G takes a leaf to a leaf. Oh, sorry, I'm calling these leaves. What I mean is R orbits. Sorry. So if you have any R orbit, gamma will preserve that, will act within it. Elements of G will move that to a different R orbit. But on each R orbit, you can look at what happens. An element of G will move it to some other R orbit. But again, instead of calling them R orbits, let me call them just leaves. Leaves are R orbits. Yeah, an R orbit in X is called a leaf. And the action, we know that the action of gamma, when we part of the construction of Z was to construct the action so that on each R orbit, gamma is Lipschitz, and that'll carry over to the induced space. Each element of G acts by a Lipschitz map on each R orbit. And it's a basic fact of analysis that Lipschitz functions are differentiable almost everywhere. So at almost every point of Z, each element of G will have a derivative in the direction of the R orbit, in the direction of the leaf. And let's just define chi of each element of A to be the integral of that derivative. We integrate over all of X, the log of the leafwise, just the derivative in that one direction, the direction of the leaf, take the derivative in that direction of this Lipschitz map, integrate that over all of X with respect to this P invariant measure. Well, because of the invariance, because we're integrating against an invariant measure, this function, which is a function from A to the real line, is a homomorphism. Usually you get a cocycle, but we're integrating an invariant measure, so we're going to get actually a homomorphism. And a crucial fact is that this homomorphism is non-trivial. You can find an element of A so that chi of A is not 0. And since it's a homomorphism, that means just by taking the inverse, maybe, we can assume that chi of A is less than 0. And let me explain why this is true. The idea is just that X is the whole space. So if you translate by A, you're still just going to get X. So obviously, I mean, I've got two sets that are the same thing. They'll have the same measure. And what that means is that if you integrate the radon-Nikodym derivative of A over the whole space, that has to be 1. The integral of the radon-Nikodym derivative is 1. But it turns out, since the action is within leaves, the radon-Nikodym derivative is just the derivative along the leaf direction. There's no stretching transverse to the leaves. It's along the leaves is where all the action is happening. And now just apply Jensen's inequality. Log is a concave function. So the integral of the log of a function is less than the log of the integral of the function, but in this case, the integral of the function is 1. So we've got this integral being negative, which is what we're looking for. Okay. Well, the thing is that this fact isn't really very useful on its own. This is not difficult. We need something more. We need to know also, in order to apply the key proposition, we need to also know that the expanding direction is the expanding subgroup is contained in P. That is not obvious. That takes much more work. It's pages and pages. Maybe there's a more straightforward way, but it's a technical fact that you need. Let me just assume it's true instead of worrying about why it's true. And then let me explain what this fact gives us. Well, first of all, of course, we've got, we've got all these elements. Let me not worry about the expanding direction. The fact that we've got chi, we've got this homomorphism chi, and it's non-trivial. There's an entire half space where it's negative. And the theorem is that for every point in that half space, every point whose average, so this Leafwise derivative is the amount of expansion. If the average derivative is negative, that means on average, A is contracting along the leaves. Well, if you take any point in X, and then another point on the same leaf as X, on average, every time you apply A, there'll be some contraction on average. In some places it's expanding, some places contracting, but on average, you'll see contraction. What that means is if you iterate, so if we don't just look at just X and Y, but look at move by A, every time you apply A, it may expand or contract, but on average, you'll see a contraction by a certain amount. So exponentially, on average, it'll contract. There's some details here, but I think it's very plausible, at least, that if there's contraction on average, then you actually see that in the long run, just by the Birkhoff-ergodic theorem, essentially, pointwise ergodic theorem. You'll periodically see these contractions, and on average, they won't get, when you look at what happens on average, you'll see contraction, so points will get contracted together on leaves. This is what I mean by leafwise contraction. An element of G, or let's take an element of A, is leafwise contracting if for almost every pair of points on the same leaf, the distance between them goes to 0 as you iterate A. That's what leafwise contracting means. And so let me now prove this key proposition. I want to prove that if it's contracting, then you're invariant under the centralizer. So let's just take an element of the centralizer. This is the key to their whole proof. If you understand why this is true, then it's clear that you have a contradiction. There can't be an action. So take an element of the centralizer. I want to show that C preserves the measure. So I want to say that if you translate by C, the measure doesn't change. You're back to the original measure. And let me remind you what this mu is. This mu P is a P invariant measure on X. And X we can think of as being G mod gamma cross Z. Well, take almost any point of X. Take a generic point of X. It should be generic for the action of A with respect to this measure mu P. Then if you just translate by C, remember C is in the centralizer, so it'll take an A invariant measure to an A invariant measure. C times X will also be generic. It's an isomorphic, but it's moving the measure from mu P to C times mu P. So it takes the action of A and moves it to an isomorphic action whose invariant measure is C of mu P. And now if we apply A to it, I mean, we're talking about generic for A, moving along the orbit's not going to change it from being generic. So this is still going to be generic, but generic points have a dense orbit. So we can choose K so that so at this point, a to the KCX, this moves around all throughout the space. Let's pick a K so that's very close to X, our original point. That's just by ergodicity here. It's going to move all over the space. Well, now if you look at if you look at this point, we've moved, we translated by C, then we moved by K. If you only look at what's happening in G mod gamma, well, this point is close to X, but it's in this crazy space here. But we don't know anything about Z. Let's just mod out Z, just project down to G mod gamma. This point, we've got 2 points in G mod gamma that are close together. In G mod gamma, this is a nice manifold. We've got A is acting nicely. Any nearby point, any point that's near to X, like this one here, can be obtained by going along the stable foliation and then along, well, I should do it the other way. You can go along the strong unstable foliation and then the stable foliation. That sweeps out an orbit, a neighborhood of X. So what that means is we can write this nearby point in G mod gamma as something in the stable foliation times something in the strong unstable times X. And here there is a technical, oh yeah, okay, and then, whoops, yeah, okay, yeah. Let me just give a name to this point. Let me just call it XC instead of having to write so much there. Now, mu P is invariant under P, but we're assuming that the strong unstable is contained in P. So this measure is invariant under the strong unstable. And that means that any co-null set essentially is a union of orbits. Any co-null set has to be invariant under this up to measure 0. So what that tells us is that actually X, we were assuming that X was generic, but we're moving by something that preserves the measure. Mu plus X is also going to be generic. Except that's not quite right because there's an almost everywhere. It's only almost every point on the U orbit is going to be generic. So there's a little technical issue here. It turns out that instead of just translating X by U, we should also this point by U, we should also apply a little element of U over here as well. You have to jiggle to avoid this null set, but it's a minor technical point. And let me just give this point a name, X0. So here we almost have the proof. We're almost done with the proof here. Yeah, okay. So now what I want to do is just look at the distance. Well, these 2 points are very close together. That's my assumption here. Yes, XC is very close to G inverse G minus X naught. But let's apply let's look at the orbit of X naught under AN and look at how that goes as we also move G minus X0. Okay, so I have 2 points. I'm going to flow them both along A. That's what I do. So I take 2 points nearby, flow them along A, but G minus here, this is in the stable foliation. That means it doesn't expand. It stays the same size. So up to, yeah, the distance here, this G minus doesn't change. We're just getting these points start out close together. Since they're connected by something, the stable foliation, they stayed close together at all times. And they started out very, very close together. They're going to stay very, very close together through their whole orbit. So these 2 orbits are close together at all times. I want to do the same thing, except instead of X naught, let's look at XC. Look at its distance to the same point. So I'm looking at the orbit. I took X naught and this thing on the stable leaf. They stay together. I'm now going to take XC and this other point on the stable leaf. Look at them as we go on. Well, let's look at what's happening here. So XC is this thing here. In G mod gamma, it's exactly the same as G minus C. On G mod gamma, these are the same point. There's no distance between them. The only distance between them is from the Z coordinate. They might be in different Z coordinates, but it turns out that in fact, they don't, in the Z coordinate, they're actually in the same leaf of the Z coordinate. These 2 differ just by being, and that's because G preserves leaves. Gamma acts within leaves. So between the two of them, these are actually, this distance is actually a distance along the leaf. These 2 points started out in the same leaf. As you flow, they'll stay in the same leaf. But we're assuming that A is leafwise contracting. That exactly means that this leafwise distance is going to go to 0. So we've got these 2 points, x0 and xc. Both of them stay close to the same point. I've got 3 points actually, but x0 stays close to this funny point. XC stays close to this funny point. All 3 of them are moving together. So x0 and xc are moving together. The A orbit of x0 and the A orbit of xc are virtually indistinguishable. They're within delta of each other, some small distance at all times. So what that means is that if you average a function over those 2 orbits, you get the same answer. They have almost the same Birkhoff averages. For any uniformly continuous function, if you take the average over an orbit of xc, you'll get almost the same answer as an orbit as the average over an orbit of x0. As you take the limit as epsilon goes to 0, you find, in fact, that the limiting averages are exactly the same. But mu p is what you get as a Birkhoff average of x0. But remember, xc, that's this point here, is generic for the translated measure. These 2 have almost the same Birkhoff averages. Well, yeah, a generic point for this has almost the same average as a generic point for that. But take the limit as epsilon goes to 0, you find out that these 2 measures are exactly the same, which is what I was trying to prove. I wanted to show that the measure was invariant under the element to the any element to the centralizer. Okay, that's all I had prepared something extra in case I had extra time, but I think this is a good place to stop, except that I do want to take this opportunity to wish Dani a happy birthday again, and also very much say that I hope we'll meet again soon. Thank you.
Any comments and questions?
Thank you, Dave. Dani from
Thank
Dani.
you. Yeah, thank you.